All right, now I've ridden on one of these before. These are really, really cool. You stand on the ground and you stand inside of this cylinder essentially, and the cylinder starts spinning around and around and around. Now, of course, because of the friction with the floor and the friction with the wall, the people inside start spinning around with it. Now, at some point, it's going so fast, the floor stops dropping out from under them. Now, the question is, how do they stay? And you can actually see it in this picture. Here's the floor down here. That's that darker gray, but none of them are actually touching the floor. They're all being held up. So how does that happen? Well, there's friction, right? It's the friction between the person and the wall. If this is the person right here, let's draw our person, and here's the wall. So this is like a person over here, all right? You can look at, you've got the force of gravity down. You've got the normal force of the wall, which is pushing this way. And then, well, if it was only gravity, they should fall down. So there must be some friction that's pushing up, holding them on the wall. And so that's what's happening. Now, what is the centripetal force here? Well, hopefully you're recognizing that the centripetal force is actually our normal force. That is the force that's actually pushing towards the middle, making them go in allowing them to go in a circle, right? So in this situation, we're going to say, well, that means that the normal force is the centripetal force. So again, we're recognizing what is the centripetal force here. Now, if we recognize that that is the centripetal force, we should then be able to move along. Now, what information is given to us? They do give us the coefficient of friction. They do give us the diameter of the ride. So we can start putting in some things, right? We know that the centripetal force is mv squared over r. Now, they did give us the coefficient of friction, all right? How are we going to figure out, because this time the normal force is not equal to the force of gravity. They're in completely different components. One's vertical, the other's horizontal. So we're not going to be able to get the normal force from the force of gravity this time, right? We're going to need to be able to get the normal force from something else. Well, hopefully you remember that the normal force is connected to the force of friction. It's that coefficient of friction times the normal force, which is equal to the force of friction. Now that we're thinking about the force of friction, notice that the force of friction has to balance the force of gravity in order for those people to stay up and not fall down. So therefore, the force of friction must be equal to mg. And so we've got the coefficient times the normal force, which must equal the force of gravity, which is mg. Now, if we divide by the coefficient, we're left with the normal force is equal to mg over mu. Now we've made a connection of the normal force with the coefficient of friction, which is what they'd given us, right? So we don't know where this is going from the beginning. I still don't know how I'm going to solve this question, but I did identify what the centripetal force was. I can put the mv squared over r in, and thinking about the things that I know, the things that I have, well, I know the force of gravity because that's going to be mg. I can connect that to the frictional force because those two are equal, and then I know that the normal force connects to the friction, and so I get this mg over mu. So I'm actually going to put that in, mg over mu here. And now we can go ahead, again, we've got those masses canceling out. You'll notice that in a lot of these situations, the mass really doesn't matter, okay? Now the question is, how fast does the ride need to be rotating? So let's go ahead and put in some numbers. We've got g, which is 9.8. We've got the coefficient of friction there, which is 0.5. We've got the v, which is what we're looking for, and the radius, which it gave us. Oh, it said the diameter is about 10 meters. So we're going to go ahead and put the radius as being 5. And so now we can go ahead and multiply, do that math. We'll just do the 9.8. We'll divide by the 0.5, and then we'll multiply by that 5 on the bottom, and we get 98. And then we square root that. And when we square root 98, we get something pretty close to 10, right? We get 9.89. So I'm just going to go that V is equal to 9.9 meters per second. All right. Now, that's only letter A. Now, we did talk about frequency in a previous class. Remember, frequency is the number of cycles per second. Well, right now I have meters per second, so I need to somehow go from meters to cycles. So I'm going to do actually a conversion here. Now, there's a number of different ways to go about this, but if you think about the dimensional analysis, you should just be able to kind of work with the units, right? How many meters are there in one cycle? Well, one cycle is all the way around the circle of a radius of 5. So circumference there is 2 pi r, which of course then is 2 times pi times 5. And so the distance of a cycle is 10 pi, or 31, I need to put meters on the bottom, and I need cycles to be on the top. So there are 10 times pi, which is 31.4 meters in one cycle. And so now I just multiply by the 1 and divide by that 31.4, and I get that the frequency is equal to, meters cancels out, I get 0.32 cycles per second, which we can use that units of hertz if we want. So the frequency is 0.32 hertz. All right, there we go. So that's cycles per second. Now, we haven't talked about angular speed yet. Now, I think now is as good a time as any. So let's chat about angular speed. So angular speed is, instead of having meters per second, we say how many degrees per second it is. Now, we can actually get that from this 0.32 here, right? We already know that there are 0.32 cycles per second. Now, what we want to do is we actually want to turn the cycles into degrees, all right? Now, you can do degrees or you can do radians. Now, actually, we're going to go ahead and do radians because AP likes for us to use radians. Now, if you don't know what radians are, if you haven't seen that yet in math class, there are 2 pi radians in one circle. It's a measure of an angle, kind of like degrees, except it's a different type of units. Just like meters and inches are different ways of measuring length, degrees and radians are different ways of measuring an angle, or how far something rotates. And so there are 2 pi radians in one cycle. And so we can go ahead and just take that number that we got and multiply it by 2 pi, and we get that we get that the speed there is 1.98, which I guess if I'm sticking to my 2 sig figs there, I'm going to end up just getting 2.0 radians per second. And that would be my angular speed though. Okay, now the reason why angular speed is interesting, the reason why we like angular speed is because for any point inside of our circle, they all have the same radians per second, right? A point here will go through 2 radians in 1 second. A point closer to the middle will go through 2 radians in 1 second. A point right next to the middle will rotate through 2 radians in 1 second. They all travel different distances, so they're going different linear speeds, right? A guy on the outside has to travel much further than something in the middle there. And you've probably felt this on a merry-go-round or something like that, on the playground. If you're in the middle, then it's really easy to hold on. But if you're on the outside, you're traveling so fast, it's hard to hold on to the merry-go-round. So the angular speed is constant for every single point on a solid rotation, right? Whereas the speed will be different depending on how far you are from the center. We'll talk about that more when we do rotational motion later this year. But for now, just be aware that we can write a speed not just as a linear meter per second speed, but we can also do radians per second or degrees per second. But like I said before, AP likes for us to use radians. All right, that's it for this one.